Good day. Um, I'm going to be discussing about a little bit more complex arbitration logic. Uh, in the previous one, I discussed a very simple arbiter. Let's make it a little bit more complex. So, as you know, the job of the arbiter is to give a grant when multiple requesters are there. Who is going to access the resource? In this example, let's say we have 4 requesters or 4 agents trying to access the memory. So which one should get a grant first? In an ideal round-robin fashion, you will circle through each one by one. But that may be inefficient. Let's say one of the requester is trying to access 128 bits from the memory, and that requester has a higher priority compared to other 3 requesters. So if you do the round robin, which means requester 1, requester 2, requester 3, requester 4, then requester 1 will have to wait till requester 2 and 3 do their job. And that creates a inefficiency or performance hit on requester 1. So in many systems where you want to give higher priority to some of the agents and the other agents could wait, then this whole simple arbitration scheme would have a significant performance hit. Let's see with an example. By the way, you can check the previous lecture with the RTL code on a simple arbitration logic on the YouTube channel. There is a link here. Also, if you go to my channel, you'll find the arbitration logic, simple arbitration logic. You can look into that. Let's understand from an example what I meant by the performance hit. Right? So let's look at that. Let's say requester 1 wants to access 128 bits from the memory. Requester 2 or agent 2 has a request of just 32 bits from the same resource. And the requester 3 is also trying to access or pass access, for example, here. And I'm not looking at the requester 4 just for simplicity. Let's say no request comes on requester 4. So in a round-robin arbitration logic, requester 1 comes first, its grant will go first. And now you see memory 128 bits are needed from the memory, but your bus can only support 32 bits at a time. So requester 1 will have to get 128 bits in 4 cycles, 4 clock cycles, right? But here, since it's a round-robin arbitration logic, and requester 1 got a grant, got 32 bits from the memory. Now it's the chance for the second arbiter now to get its 32 bits. So we give a grant to second arbiter or second requester. So as you can see here, the grant we had given to the first one, then the second one, and now the third arbitration for the third requester comes in third clock cycle or T3. All right. So now once this, and there is no request on requester 4. So once the all the first request of all the agents or requesters is fulfilled, then it go back in a round-robin fashion to see if any more is pending. Now, as we said, the requester 1 or agent 1 needs 128 bits, so its request will be active high, pending, to wait for the next grant. So here, once all the active requesters request is granted, in the first phase, because it's a round robin arbiter, we give the grant to requester 1 again. And at that point, now we look at the second one. There is no request pending from the second one, no request pending from the third one. So we give grant again to the requester 1. And since no more requests are pending from requester 2nd, 3rd, and 4th, we give another grant to requester 1 till its request is high or any other requester requested. And here it completes its 128 bits from the memory. So now let's see what happens here. Okay, so requester 1 took almost so it had to wait for 3 cycles here, T1, T2, T3. So it created a bubble of 3 clock cycles. It could have been done, let's say 32-bit wide is the bus, 128 bits are needed, 32 multiplied by 4 is 128. So 4 clock cycles are really needed, and it doesn't have to wait. But since the requests were there on other requesters, it had to wait. So that created a bubble, and that bubble on requester 1 or agent will hit the performance heavily in a bigger context or bigger system design. So we understand now, because of the bubble, there is a performance hit. Is there any way we can improve the design? And we improve the design in such a way that we not only give the priority to the requester 1, but at the same time, it's not that the requester 2, 3, and 4 are starving. So we need to have some ingenious way of handling it. You may find many algorithms and many more ways in research articles. My purpose here is to make it simpler, and in order to make the concept understood, I give here a simple example. So let's move forward and see how can we improve it. What if we give some credits to each of the agents? Okay, so let's initialize each requester with some credits. Okay, and we decrement the credits with each grant respectively, and we keep giving the grant until requester has positive credits. So what will happen when we assign the credits? And you can actually give you can decide how many credits you want to give to each requester depending upon how much priority you want to set. You can think of it in form of a priority, but essential idea is that you can program the credits via software, initial credits, and sometimes you want to have higher credits for requester 1, but then you may want to change the credits and give priority to the, let's say, requester 3 or requester 4. Software can program. So it's a very good way, ingenious way to assign initial credits, and then the credits will get decremented with each grant, and as long as requester has a positive credit, it will have the higher priority compared to other requesters, and it should improve the performance. And you can change the priorities of different requesters, so it's not like a fixed priority. So in a more dynamic way, you have a more control on changing the priorities and improving your system performance overall. So let's see with an example how this overall scheme is going to work. By the way, I forgot to mention that once the each requester credit counter or credit is 0, which means that requester has no more credits that its grant will be allowed, then the number of other requesters come. So once all the requesters have eaten up their credits, or layman's language, eaten up their credits, but you may also say in a more refined way, when all requesters' credits are burned or all requesters' credits have been consumed, then you can reinitialize the credits to their initial configured value via software programmed registers. Okay, so once all the credits are 0, all the requesters' credits are 0, since we are decrementing, at that time we reinitialize the credits. Okay, let's see, for example, requester 1 or agent 1, I assign credits for requester 2, 3, 1, and 4, 2. So let's just say this is the initial value of the credits. You can imagine if there is a 32-bit register or 16-bit register, you can have much more higher values. But then you have to really balance out, because if you give too many credits to requester 1, then other requesters will have to wait till requester 1 credits are consumed. So you got to be mindful on that before programming that what exactly system-wide, how much performance hit you want to improve. Because if you give too many credits to requester 1, then other requesters would be starving, right, until the requester 1 credits are finished. But sometimes you just want to have highest priority to requester 1, and you have more data flow going via agent 1, and other requesters or agent can wait, then you may change. Okay. And config registers or configuration registers for any IP, they're programmed via firmware. So you can initialize the registers, and your design should take the initialized value from the register. So let's see an example here, how we improve the performance. Same example where requester 1 need to access 128 bits of the memory, and requester 2 wants to access, let's say here, 64 bits from the memory instead of 32. I just say 64, just to show an example. And requester 3 has just 1 credit. Okay. So what happens? Requester 1, round robin algorithm, on the improved one now with the credits. So we see that, okay, who has the highest credits? Here, requester 1. We give grant to requester 1. Okay, and we decrement its credit. Now its credit is 3. Okay. So since it has positive credits, you can make it more complex. You can compare, credits at each clock cycle with other arbiter, but that's the extra complexity. Very simple way that each clock cycle, each grant actually, you reduce the credits. You decrement the credit by 1, or whatever number you may want to decrement. Here, I'm just assuming 1, decrement by 1. So another 32 bits are fetched from the memory. Still the credits are positive. Give another grant. Another 32 bits are fetched from the memory. Then you decrement the credit. Now the credits are 0, and you have fetched the last 32 bits from the memory. So that completes the 128 bits which requester 1 really needed without having any bubble or anything. So in 4 clock cycles, 128 bits are fetched. Better performance. Now it has run out of credit. Now we look at the requester 2, 3, 4. So requester 2 here needed to access 64 bits from the memory, and it has 2 credits. So we give grant to requester 2, decrement its credit by 1 in the next clock cycle. Let's say whether the request from the requester 2 is pending. Yes, it is pending. Now requester 2 gets a grant, fetch another 32 bits. That completes its 64 bits, and its credits are 0 now. It consumed all its credits. Okay, no more grants to requester 2. Now we come to requester 3. Requester 3 has 1 credit and a request. So we give grant to requester 3 and decrement its credit. Once we decrement its credit, it becomes 0. So at that stage, all the requesters have consumed their credits, or their credits become 0. At that stage, we should reinitialize it from the configuration register, their credits. Okay, so in the next clock cycle, which is T8, we initialized their credits once they run out of their credits. So in this mechanism, you have improved the performance on the requester 1. At the same time, other requesters are not starved forever. A much better design than the simple arbitration logic. Okay, there's no bubble, improved performance. All right, very good. Now let's look at let's look at the design. So first thing should come to mind that the basic simple arbitration logic, we want to improve it. So we may need more registers here, and we also need to store the credits. We also need the previous grant to be stored, and a few other registers for the state. Okay, this is a schematic representation sort of picture should come to the mind. Okay, now let's look at the Verilog code, or system-verilog code, how we can develop it. I have written the code in advance, but I will walk you through the code. As you can see here, package, similar thing what we did in the previous example. This line number 11 is taking the configuration register, all of the configuration register, and this is a type CFG_T. We are so all the register values, and then we can pick up the credits from that package and assign it, because remember what I said, once all the so first initialize the credits. Okay, once the credits are consumed, then design should reinitialize from the config register. So we need the config registers here, and the request type is ARB_T. I'll come to these types in a minute, and then the grant and clock reset. See, use the packages, right? Pack your signals in packages is a much better design practice. Clutter free, you will write a good code. You have some internal signals for so when I say _FF, which means that my intention is to create a register here to store the values for what was the previous grant. Okay, so we have number of requesters. It's 4 requesters. So what was the grant state for these requesters? Okay, and then the credits. Okay, so grant becomes important. Previous grant, right? For each requester, and then I have this function. Function is defined in the package, which takes the request and the previous grant and the credits, because we're going to be storing, decrementing the credits for each requester. So we would need the credits here. And how the credits are decremented, I did write in line number 26 just for one arbiter, and then you can loop it through. So more refined version on 27 where you are using generated statement and looping it through. So if the grant is high, then what we are doing here, decrementing the credit, okay? Because we said with each grant, we're going to decrement the credit. Otherwise, if all of the requesters grant is 0, okay, so which means that reverse is 1, so which means that all of the I think there is a mistake here. This should not be the grant, this should be the credit. And all of the requesters credit is when all of the requesters credit is 0, then we initialize it with the configuration registers. Otherwise, we just keep it the previous value. So this statement here needs to be corrected. So when each requester is run out of their credit, then only we reinitialize. Okay. So this was for a D input to the flip-flop. Think about the line number 26 and 27 is the D input to the flip-flop for restoring the credit. So once we have the credits here, then the flip-flop, right? So flip-flop is simple way that line number 34 is just for one requester, that the D input to the flip-flop and then the Q input to the flip-flop. This is a template. I did write more in the package file. I defined this FFR, and then once you have established for one, then you can circle it through via generate loop. Okay, you define the gen variable, and for each requester, or just simply saying the D input go to the flip-flop, and then the Q output here underscore FF and the clock and reset. Okay. And because we have just a grant register which gonna store the previous grant for each of the requester, so you just need one more register here. And each grant you can just grant it out to the output. So look at the code. Look at the code within 50 line, or within few lines. 50 is just line number, but there are a lot of space and comments here. The line number 24, one line for the grant or previous grant with the function, and then line number 27 and 35. See how simple is the code? Very clean, simple. So you are decrementing the credit on line number 27. Okay. Line number 35 is creating a register to store the credits, and line number 24 is taking a decision when to give a grant. Wonderful. Now let's look at the package file. Okay. Now let's look at the package file. Important here is the line number 15. Where I'm just saying that you may have some other configuration register or something else. You just define a register underscore T as a type, and then you have credits type. Here I'm defining type that I have the 4 arbiters, and I'm just giving each arbiter how many credits, so 3 down to 0, right? Um, how many? 16 would come maximum value with the 4-bit register. So each of the requester can go maximum 16 credits because I'm using here 4-bit register. But by standard, you may use 32-bit register or 16-bit register. The more you're going to use, more it's going to create the hardware, right? So be mindful while using the registers. Do you really need the big 32-bit register, or you can get the job done with a less bits. Now here, if you look at it, 4 bits for each of the arbitration logic, so 4 multiplied by 4, 16 bits total, right? So you can use it as 16-bit, right? When the synthesis tool will do it, it most likely will generate a 16-bit register internally for each of the requesters credits. So here, then CFG underscore T is another CFG underscore T, another package where you are taking some of the other configuration registers plus the credit register values. Okay. All right. Other items here in this file are from the previous example. Now let's look at the function here. So line number 28 was a simple arbitration logic function. Now this we discussed in the previous lecture. You may look at more details. I would be discussing now line number 51, that function where we have issued the grant and with the credits. Okay, so we are taking a request, 4 requesters, and what was the grant, previous grant, and what are the configuration register for sorry, not here configuration register, but here what are the credits for each requesters. Okay, so simple. Previous grant mask, we just improved the logic from the simple arbitration logic, that keep giving grant to that particular requester as long as their credits are positive. So if their credit is positive, then just keep giving the grant to it, irrespective of what other requesters have the request. And once the credits are 0, okay, then don't give it the grant. Okay. Now let's look at the second one. So when the second requester comes in, as long as the credits are positive, keep giving requests to the so I think I made a mistake on this, because really no, not really, that is correct, because we are doing a case here, and when the second previous grant comes to the 01, then we give okay. So here we are creating a mask actually. So this code is correct because the mask would be used to give a final grant at line number 64. So we updated from the previous simple arbitration logic mask to a more complex arbitration logic where we have the credits. So the line number 58 to 61 are just updating the masks. So as long as the credit is positive, then just keep giving the request to 1. So its mask would be 0001. And similar thing for the arbitration logic on the arbiter 2 or requested 2, that if its credits are positive, then just keep giving request to it, others are 0. So the mask we are updating here. Okay, so all 4, and then the arbitration request is now masked, okay, with the input request. Okay, and the grant, which one will get a grant? So if the arbitration request 0, okay, after the masking is true, then we give the request first requester to the grant, okay, the very first grant. So the line number 43 to 46, they didn't change. Only from the simple arbitration logic, only the change is in the mask, because mask is really deciding which one would get the grant. Okay, so we update the mask, and rest of the logic is same. Okay, good. So line number 66, 69, 70 from the previous example, it's all going to be same. So essential idea here is that we updated the mask criteria, right, with the credits, and we updated the logic when to decrement and how to decrement the credit. Okay, very simple. And now let's look at the compilation here. Let's see, oh, did I make a mistake here? So it's a good tool. I think I made a mistake. Let me put it, mistake is saying at line number 27 in this file, 7. So here, credit, I think it is a syntax error. It should be credits underscore FF. All right. Now let's compile it again. Wonderful. No lint errors, no syntax error. Now let's say we have build. Okay, let's build it with the CPP file, Verilator CPP file. I explained on these files arbitration logic and CPP file, but just to show again. So you may have to have same file for each of your module, or you may find some other way to do it, but here simple. Wherever V stands for is Verilator, and then HRB credits, ARB credits, HR. This is the module name. And then you're referencing Verilator.h, and line number 6, where you will change the module name. Okay, and then rest of it is standard Verilator related. This is an example for the CPP file which you need if you want to build the code. Most of the time I just use lint, but to explain here. Let's say Verilator. Hyphen cc hyphen exe hyphen build is gonna build the code, and it has put it associated files in obj directory, and once you see the harb credits, they say executable file, so you can execute it. I don't have anything here in that file, but you can put messages, or you can develop a test bench code to further simulate it. All right, thank you. Let me know your question, comments. Hope this has contributed to your learning. Good day. Thank you.